Hey there, this is the video for Chapter 2, Section 2. This section is all about graphs and charts, so you'll be doing a lot of number crunching and working with technology. You'll need both your calculator and access to the course website, which has a program called StatCrunch on it, so make sure you have access before you get settled. I'm going to walk you through the process for each one, and there are some instructions for creating them in the lecture notes, but feel free to pause the video and take extra notes on the steps where you need to, because I guarantee I'll be asking you to create or at least analyze more of these in the future. Speaking of which, yes, I am expecting you to create these graphs and charts in the lecture notes. Wherever it asks you to create something, I need to see something that you created. It doesn't have to be perfect. I'm not expecting exactly straight lines or anything like that, but you need to put in the work. Plus, doing it helps you remember it. Okay, let's go. Hello everyone, welcome to Chapter 2, Section 2. This is an extension of Section 1 in terms of exploring ways to visualize a frequency table. Creating graphical representations of quantitative data is part of what statisticians call exploratory data analysis. We already covered a handful of methods in the first video: histograms, frequency polygons, relative frequency histograms, and ogives. Now the graphs I'm about to show you are going to seem pretty rudimentary in comparison to the ones we've done so far, but simplicity shouldn't imply that they are of any less importance. The graphs we're going to cover today, while simple and easy to construct, can be hugely instrumental in revealing the big picture that any raw data set might be concealing if left unorganized. We're going to cover graphing and interpreting quantitative data using stem and leaf plots and dot plots, how to graph and interpret qualitative data using pie charts and pair 2 charts, and how to graph and interpret paired data sets using scatter plots and time series charts. So let's get started. Let's start with the stem and leaf plot. Each number is separated into a stem and a leaf. If you look at the picture, you can kind of picture it like a tree stem with leaves. The stem is the tens place, like the numbers 8, 9, and 10 here, and the leaf is the ones place, shown here by several values. An important thing to note is that the tens place, or the stem, can be represented by one or more digits, as the example shows, whereas the ones place, or the leaves, will always be a single digit. Just like on a tree, there are many more leaves than there are stems. A stem and leaf plot is very similar to a histogram in structure. If you tilt your head to the right and look at the plot that way, you could almost see each row as a standing rectangle. The stem and leaf plot method of organizing data still keeps all of the original data points. Being mindful of that, you do want to keep track of any multiples on this type of graph. See how there are two 86s? We represent them with two 6s next to the 8 stem. And lastly, a stem and leaf plot provides an easy way to sort the data. So how do we construct a stem and leaf plot? Let's walk through the process of creating one from scratch. Here we have a data set that lists the numbers of text messages sent in one day by 50 cell phone users. Display the data in a stem and leaf plot. Describe any patterns. Let's practice displaying the data in a stem and leaf plot. Right away, I can see that there are stems that will be one-digit numbers and stems that will be two-digit numbers. See the 75 and the 104? The 75 will be represented with a 7 in the tens place, or the stem, and a 5 in the ones place, or the leaf, and the 104 will be represented with a 10 in the tens place, or the stem, and a 4 in the ones place, or the leaf. What you want to remember is that the rightmost value, the leaf value, is always just one digit. It's okay that the stems have different numbers of digits. Leaves just have to be one digit. Our next thought might be, what stems do I need? I know I need a 7 for the 70s and a 10 for the hundreds, like 104, but what other values do I need? It's at this point that the calculator becomes your friend. It may seem tedious when you're first getting used to it, but if you had to keep track of these numbers by hand every time and list them out in a stem and leaf plot by hand every time, it would get old really quickly. So though it may seem like a lot of work at the beginning, trust me that you'll appreciate getting to know how to do these things on your calculator. So let's learn how to do that. The great thing about the statistics functions on the calculator is that it's a very easy process to enter numbers into lists. All you have to do is press Stat, make sure Edit is selected, and press Enter. Then put your data points into L1, pressing Enter in between the numbers to progress. Pause the video and do that for these numbers now. You can enter them top to bottom or left to right, whatever works for you. Your calculator will do the sorting for you later. By the way, I haven't mentioned this before, but if you need to clear entries from a previous exercise, all you have to do is arrow up to where you have L1 or L2 highlighted or selected and press the clear button on your calculator, then enter. This will clear the whole list so you can start over. Do this for both L1 and L2 if you had values in there before. Also, in case you're wondering when entering, yes, you do want to enter multiple. It's okay to have more than one of a number. In fact, you need to make sure you include all of them so we're representing all of the data entries. So, pause the video now and enter these. Great, so you've got those entered? Just another machine for your thumbs to become experts at typing on. I'm sure you'll get faster than me in no time. Now we have those entered, press the second button, then the Stat button to get to the list menu, then arrow over to highlight Ops, OPS. This is the operations menu for manipulating lists. Now hit Enter while it has the command Sort A selected. The Sort A command means sort a list in ascending order, least to greatest. So now we need to tell it which list we want it to sort. So we're going to hit the second button and the number 1 to select L1 above it. Then the close parentheses, that's just above the 9 key, then Enter. Once your calculator says done, go back into your list by pressing Stat and select Edit by pressing Enter. And admire the work your calculator just did by putting those in order for you. If you scroll down, you can see what stems we would need for a stem and leaf plot. 1 for teens, 2 for 20s, all the way up to 10 for the 100s, 11 for the 110s, 12 for the 120s, 13 as a placeholder for the 130s, and 14 for the maximum number of 148. Now that makes it easy for us to do the stems because we sorted the data. We actually have less to do to organize the leaves too because they're already in order. We can see exactly what leaves go in what order for each stem. Make sure you're taking good notes on these calculator instructions and putting them somewhere easy to find. Those will come in handy later. So let's put this all together now. List the stems 1 to 14 left of a vertical line for the stems. Then you'll put all the 1s to the right side of the vertical line to represent the leaves. Make sure to the side a little bit you put a key that makes it clear what someone is supposed to do with a stem like 10 as it's shown here. One thing I didn't mention before, but you'll see in other examples, is that you can do a stem and leaf plot for decimal numbers as well. You can use the vertical line as the decimal place and have everything to the left of the vertical line be what is to the left of the decimal point, and everything to the right of the vertical line be what is to the right of the decimal point. Just make sure you include a key like this that makes it clear what the vertical line represents. Back to the data we're working on now. Now, what can we gain from sorting data this way? What patterns become apparent? Well, for one thing, it's easy to see that more than 50% of the cell phone users sent between 20 and 50 text messages because that's where all our leaves are, our data entries. The data is definitely right skewed. Now, how can I tell it's right skewed if it's vertical? Well, just tilt your head to the right and look at it like a histogram, as we did at the beginning. You can clearly see the tail of the data entries trailing off to the right. That is right skewed. Also, we included 13 even though there wasn't a leaf for that stem, and it's important to do so we can visualize that gap in the data. So make sure you don't skip any stems when writing out your plots. There are other variations of the stem and leaf plot, including doubling the lines of data. This is done if you want to really break down where the data entries fall. This is done by having 2 lines for each stem and putting the leaves that represent data points for 0, 1, 2, 3, and 4 on the first line, and leaves for data points representing 5, 6, 7, 8, and 9 on the second row. This gives you a more detailed picture of the data. Okay, I think we're ready to move on from stem and leaf plots onto another type of graph. Dot plots are simple in concept, but they provide a lot of information, so they can be very valuable. Each data entry is plotted using a point above the horizontal axis. See how the 26 has a dot above the 26? Each value in the data is represented this way. Like the stem and leaf plot, a dot plot shows you how the data is distributed. It retains specific data entry values, and it helps us to quickly identify outliers. Here's a quick example. Notice that dots are stacked on top of each other for values that repeat, like you see on the plot for 25. And for other areas where there are no data entries, say for example this data has no data values between 31 and 35, we don't have any dots in that whole area of the plot. Here's the data set from the first example, number of text messages sent. And here's the dot plot for that data. This actually is an adjusted dot plot because having every single unit would make the plot too wide to really see anything, so I've done it by fives. But you still get the idea. You can see how a dot is placed at its value, and where there are repeated values there are multiple dots vertically. You can also get a good feel for the layout of the data as a whole. Notice in this example you can see where the majority of the data falls on the plot and where there are outliers. Most entries occur between 20 and 80, with only a few people sending more than 100 text messages. We call those outliers. You can also see that 148 is an unusual data entry. Did you know that my math lab has a mini version of Excel that can help make stem and leaf plots and dot plots? Let me show you how to do that. From your course homepage, click on the tab in the left-hand menu that says StatCrunch. Then click the blue link that says Visit the StatCrunch website. From here, you'll want to click on a button at the top that says Open StatCrunch. This should take you to a grid-like page that looks kind of like an Excel workbook page. You're going to want to enter all of your data into the first column called var1, meaning variable 1. After you've entered your data, click the Graph menu, and for this example, select Stem and Leaf. This will bring up a window with some options. For all the graphs you do on StatCrunch, you're going to want to select the column where you put your data. And since we put data into var1, we'll select that here at the top. Then we have a few more choices we need to make. I want to deal with whole numbers, so I want my leaf unit to be 1. And I want to see the effect of outliers, so I select None on outlier trimming. Then click Compute. Here is a shortened version of the stem and leaf plot we did before. What if I wanted to do a dot plot? We can actually use the same data and create a different graph by clicking the X to close this graph, then selecting the Graph menu again and picking Dot Plot. Even though this may seem like a simpler graph, there are more options for this one, so let's go over a few of the choices you should make. 1, you need to select the column where your data is stored, which is var1. Next, for the grouping option, it should already have selected plot groups for each column. I usually want my point size to be between 4 and 6, depending on how big my data set is. Next, whether you show the mean and median is up to you, but in this instance, I want to see how outliers are affecting those numbers, so I'll put a check next to both. I want to click None for dividers, and finally, type in a label for the x-axis, y-axis, and an overall title for the graph. Then click Compute. Here's a shortened version of the dot plot we did previously. Notice how the mean, the green line, is to the right of the median, the red line. The outlier of 148 and the other few out that direction are pulling the mean to the right, but they don't affect the median at all. You can really see that effect when there are more data points like this second example. Alright, so we've done some extensive work with quantitative data. Remember, that means numerical data. What about qualitative data, categorical data? How do we show that graphically? Well, the answer is simple. We show it as part of a whole. One of the best ways to do this is with a pie chart. It may have been a while since you've constructed one of these, so let's talk about that. The pie chart provides a way to present qualitative data graphically as percents of a whole. A circle is divided into sectors that represent categories. The area of each sector is proportional to the frequency of each category. Let's create one. The numbers of earned degrees conferred in thousands in 2019 are shown in the table. Use a pie chart to organize the data. So in 2019, there were 1,037,000 associate's degrees, 2,013,000 bachelor's degrees, 834,000 master's degrees, and 188,000 doctoral degrees or PhDs. To set up a pie chart, we need to figure out the relative frequency or percent each category makes up out of the whole. First, we want to find the sample size by adding up these amounts. When we sum up these amounts, we get a total of 4,072,000 people. Now again, because this table is in thousands, we can simply write 4,072. Now to get relative frequencies, we need to divide each of these numbers by that sample size. So we can take 1,037, divide it by 4,072, and we get 0.255. When we divide 2013 by 4072, we get 0.494, and so on, and do this for the rest of the list. After we have all of our relative frequencies, we can multiply those decimal amounts by 360 degrees to get a measurement for the central angle of the circle that represents each portion of the whole circle. Here's what we end up with. 0.255 times 360 degrees gives us a central angle for the associate's degrees of 91.8 degrees. 0.494 times 360 degrees gives us a central angle for bachelor's degrees of 177.8 degrees. And you would do this for the rest of them. And here's how we represent that on a graph. Now, unless you have a compass and a protractor handy, this may be tough to do by hand. Let's try this on StatCrunch. If you figured out your relative frequencies, multiply them by 100% to get percentages, then follow these directions. Open StatCrunch the way we did before. Click StatCrunch on the left menu of your course main page, then click the StatCrunch website link, then click the yellow Open StatCrunch button. Once you're in the program, enter your percentages in the bar 1 column. Enter your categories in the bar 2 column. Then click the Graph menu. Select Pie Chart and select With Summary. Now you need to make a few choices. To tell the program that you have categories in the second column, under Categories In, select bar 2. Under Counts In, that's your percentages, select bar 1. Under Display, select percent of total, then type a title for the overall graph. Now click Compute. Here is the resulting pie chart. What conclusions can we draw? Well, we can see from the pie chart that almost 1/2 of the degrees conferred in 2019 were bachelor's degrees. An even easier way to display qualitative data is to use a pair 2 chart. A pair 2 chart is an actual bar graph where the height of each bar reflects frequency or relative frequency. These graphs are especially beneficial in that they illuminate the few categories that represent the majority of the data. You may be looking at this and wondering why we're learning a different histogram, but this is not a histogram. It is different in 2 key ways. First of all, the bars do not touch. This type of chart represents categories, so there is no continuous data that requires the bars to flow seamlessly together, so the bars are separate. The second difference is that in a pair 2 chart, the bars are arranged specifically so that they are decreasing in height, with the tallest bar positioned at the left. Also, since this chart is for qualitative or categorical data, the labels on the horizontal axis across the bottom will be categories, not numbers. Alright, let's do an example. In 2019, these were the leading causes of death in the United States: accidents, cancer, chronic lower respiratory disease, heart disease, and stroke or cerebrovascular diseases. Use a pair 2 chart to organize the data. What was the leading cause of death in the United States in 2019? Well, you could look through the numbers and find out this information, but a pair 2 chart will give us more thorough information. And if we had more than just a handful of data points to consider, it would be much preferred over trying to figure it out by sight alone. In order of descending height, we have heart disease as the leading cause of death in the U.S. in 2019, capping off at 659,041, then cancer, accidents, chronic lower respiratory disease, and finally stroke. Besides just what the largest category is, heart disease, what else can we glean from this chart? Well, we can see that heart disease and cancer cause more deaths than the other 3 causes combined. Okay, we're going to round out this section by talking about paired data sets, where each entry corresponds to an entry in a second data set. If you've ever seen a scatter plot, then you've seen a paired data set. Each point in a scatter plot is graphed using a coordinate pair. The x-coordinate measures an entry from the first data set and measures the horizontal distance, while the y-coordinate measures an entry from the second data set and measures the vertical distance. Plotting all the information together shows the relationship between the two quantitative variables. Here's a very simple scatter plot example. The British statistician Ronald Fisher introduced a famous dataset called Fisher's iris dataset. This dataset describes various physical characteristics such as petal length and petal width in millimeters for 3 species of iris. The petal lengths form the first dataset and the petal widths form the second dataset. Again, each point in the scatter plot represents a coordinate pair in the two datasets. The x-coordinate represents the measurement of the petal length, and the y-coordinate is a measure of the petal's width. After measuring the lengths and widths of petals from lots of the same kind of flower, the resulting scatter plot was created. By the upward trend of this plot, we can conclude that as the petal length increases, the petal width also increases. To wrap up, let's look at a popular and well-known kind of paired data set called a time series graph. Time series graphs look much like scatter plot we just saw, but with a slight difference in the horizontal axis. In a time series graph, the data set consists of quantitative measurements taken at regular intervals of time, hence the name time series graph. The x-coordinate of each data entry shows us the time that the data was measured, while the y-coordinate shows us the value of what was actually being measured. For example, we could create a time series graph to show precipitation for each day in a month. Often, time series graphs start out as tables or recordings, and they are translated into rectangular coordinates. For example, this spreadsheet tracks the number of motor vehicle thefts in millions and burglaries also in millions in the United States for the years 2009 through 2019. How might we create a time series graph for this data set? The horizontal axis would represent each year, and the vertical axis would represent the number of motor vehicle thefts in that year. Thus, we get a list of ordered pairs to plot. Then, because this is in consecutive order of years, we can connect the dots and make a line graph. With all the ordered pairs plotted together, we can see that the number of burglaries remained the same until 2011, and then decreased through 2019. That brings us to the end of this lecture discussing stem and leaf plots, dot plots, pair 2 plots, and paired data sets and time series graphs. I hope you appreciated the calculator and StatCrunch tutorials included in this video. Feel free to practice those on your own and let me know if you have questions. I'll see you in the next video.